Hello good people, I'm going to talk a little bit about electron configurations within an atom. Why do we need to worry about electrons in the first place? It turns out that electrons play a very important role when it comes to chemistry. They determine chemical properties as well as where and how chemical bonds form between different atoms. So this means that we need to know a little bit about the electron. Previously, I mentioned that within the center of an atom, we have a nucleus. And the nucleus is made up of protons and neutrons. The electrons exist somewhere around the nucleus. And previously, I mentioned that we can think of it as an electron cloud. This does not mean that there is actually a cloud of electrons around the nucleus, but rather that this cloud that I have drawn here represents a volume of space where the chance of finding electrons is high. So let's say I'm talking about a hydrogen atom. A hydrogen atom only has a proton in the nucleus, and it has only one electron. So that electron might be here, or it might be somewhere else within the cloud. So instead of being here, maybe it's closer in like so, or possibly further out like so. However, surprise, surprise, there is more to this story. It turns out that this electron cannot truly be anywhere in this cloud. There are only certain distances from the nucleus that are actually accessible to the electron. So what do I mean by that? Well, in order to hopefully explain this, I need to introduce the Bohr model. So let me slide a little bit to the right, like so, and introduce the Bohr model of the atom. And here it is. So we are looking at the Bohr model. It is named after the Danish physicist Niels Bohr. Around the start of the 20th century, Niels used sophisticated mathematical methods to correctly determine some of the properties of the electron around the hydrogen nucleus. He determined that the electron can only orbit a certain distance away from the nucleus, and that each orbit is associated with a certain energy level. From the point of view of the electron, this means that the further it is from the nucleus, the more energy it requires. Each energy level is assigned a principal quantum number. The designation for the principal quantum number is n. Principal quantum number sounds very scary, but really, it is just a whole number, an integer. So n can be 1, 2, 3, 4, 5, and so on. It cannot be 1.2 or 2.4. It can only be a whole number. How does that look on our model on the left? Well, each orbit or each circle is designated with a principal quantum number. So the innermost orbit is n equals 1, or principal quantum number 1, or energy level 1. The next one is n equals 2. Then we have n equals 3, and then we have n equals 4. In case of hydrogen, with only one electron, the electron will occupy the first energy level. However, it does not have to stay here. If I provide the electron with energy, the electron will be excited from its ground state into an excited state, and it will move from the first energy level to the second energy level. Maybe something like this. So now this electron is in an excited state. And if I provide it with more energy, I could move it to level 3 or level 4. By the way, I can go straight from level 1 all the way up to level 4 if I provide enough energy. The key message here, though, is that the electron cannot be excited in between. So it cannot exist between energy levels 1 and 2 or energy levels 2 and 3. It has to be either in energy level 1, 2, 3, 4, and so on. So what happens to the electron in the excited state? Well, eventually it will drop back to its ground state. And as it does that, it will release energy that it initially absorbed when it was excited to the excited state. The energy absorbed and released by electrons is in the form of light radiation. In fact, the colors that we perceive around ourselves are due to continuous excitation and relaxation of electrons that release the energy in the visible spectrum. But that is a topic for another time. For now, I want to talk a bit more about these orbits. Remember, this is just a model, a way we can think about things. The electrons do not actually form circular orbits around the nucleus. These rings, these orbits, help us visualize the energy levels. And speaking of energy levels, sometimes they are referred to as shells. So let me write that down here in brackets as well. We can talk about energy levels, or we can talk about energy shells. All right. Now, with the hydrogen, the situation is relatively straightforward. There is only one electron that we can play with. But what about atoms that have more electrons? How does this model look then? Well, let me get rid of this writing, like so, and now I'm going to talk about atoms with many electrons. So Niels Bohr used sophisticated mathematical equations to calculate the energy levels that an electron can occupy. Similar equations have also been used to determine how many electrons each level can actually accommodate. So at energy level 1, we can have 2 electrons. So I'm just going to draw them in. At energy level 2, we can have 8 electrons. So let me draw those in. It's 1, 2, 3, 4, and so on. So far I can say when n equals 1, there will be 2 electrons. When n equals 2, there will be 8 electrons. What happens when n equals 3 and when n equals 4? Well, when n equals 3, there can be 18 electrons. And here they are. When n equals 4, there can be 32 electrons. And here are those electrons as well. There are energy levels beyond 4, but for now we are not going to worry about them. Finally, I would like to foreshadow some things. So remember, n stands for principal quantum number. The fact that this is called the principal quantum number suggests that there are others. There is L, which gives the angular momentum. There is ml, which gives the magnetic quantum number. And finally, there is ms, which gives the spin magnetic number. Now, these sound very scary, and they also sound like they've been made up by somebody who really likes the word quantum. But what do these numbers actually represent? The principal quantum number represents the size of the orbit. The bigger the number, the bigger the size, the greater the energy level. The angular momentum represents the shape of the orbit. Remember, these orbits are not actually circular. They have a certain shape. The magnetic quantum number represents the orientation in three-dimensional space. You can think of it in terms of which way is the orbit facing. And finally, the spin magnetic quantum number is describing which way an electron is spinning. So we can think of it in terms of up and down. An electron can either spin up, and I can indicate it by this half arrow pointing up, or it can spin down, and I can indicate it by this half arrow pointing down. We will explore these 4 quantum numbers in future videos. In summary, an electron can only be a certain distance from the nucleus. We call these distances energy levels or energy shells, or sometimes we refer to them as orbits. But they are not circular in shape. The electrons can move from energy level 1 to energy level 2. However, they cannot be at energy level 1.2 or 1.3 or 1.4. It has to be a whole number. The innermost orbit is the one of the lowest energy level. The further out you go from the nucleus, the more energy the electron needs to actually occupy that energy level. When an electron moves from level 1 to level 2, 3, or 4, we say that the electron is excited. And finally, there is a limit to how many electrons each energy level can actually accommodate. As indicated earlier, there is much more to this story. But before you go screaming into a pillow, that is all for now, and I will see you on the flip side.